Welcome to this coding problem walkthrough. Today, we'll be tackling LeetCode problem number 744, titled Find Smallest Letter Greater Than Target. This problem is a great exercise in binary search and array manipulation. Let's dive in and explore the challenge together. In this problem, you're given an array of lowercase English letters called letters. This array is sorted in non-decreasing order, meaning the letters appear in ascending order or remain constant if repeated. Along with this array, you're also given a single lowercase English letter called target. Your task is to find and return the smallest letter in the array that is strictly larger than the given target. If no such letter exists, meaning all letters in the array are less than or equal to the target, you need to wrap around and return the first letter of the array. The input guarantees that the array will always have at least two different letters. For example, if letters is C, F, J, and target is A, the output would be C because it is the smallest letter greater than A. Let's see more examples to clarify this further. Consider the first example. The input consists of letters equals C, F, J, and target equals A. The goal is to find the smallest letter in the array that is greater than A. Looking at the array, we can see that C is the first letter that satisfies this condition. Therefore, the function should return C. This demonstrates how we check each letter in the array to find the smallest one that is strictly larger than the target. Another example is when letters equals C, F, J, and target equals C. Here, the target is C. Since we are looking for the smallest letter strictly greater than C, we skip over C itself and move to the next letter in the array, which is F. Therefore, the output in this case would be F. This highlights the importance of the condition that the letter must be strictly greater than the target, not equal to it. Now, what happens if the target is larger than all the letters in the array? For example, consider letters equals X, X, Y, Y, and target equals Z. In this case, the target is Z, which is greater than every letter in the array. When no letter in the array is larger than the target, the problem specifies that we must wrap around to the beginning of the array. The first letter here is X, so the output should be X. This demonstrates the wraparound behavior when no valid letter exists beyond the target. Additionally, there are some constraints and edge cases to keep in mind when solving this problem. For example, if letters equals A, Z, and target equals A, the array contains only two letters. The target is A, so we are looking for the smallest letter strictly greater than A. The only letter larger than A in this case is Z, so the output would be Z. It's also important to handle other edge cases, like repeated characters or when wrapping around is required. With these examples and constraints in mind, you're equipped to understand the problem requirements and think about how to implement an efficient solution. To solve the problem of finding the smallest letter greater than the given target, the simplest approach we can consider is the brute force method. The intuition here is straightforward: iterate through the letters array and check each character to determine if it is greater than the target. As soon as we find such a character, we return it as our answer. If no valid character is found during the iteration, we account for the circular nature of the array by returning the first character of the array, letters, 0. Now, while this method is easy to implement, it has trade-offs. The time complexity is O(n), because we may need to traverse the entire array in the worst case. The space complexity, however, is O(1), as no additional memory is used. The pros of this approach are its simplicity and ease of implementation, but the major downside is its inefficiency for large arrays, as it relies on a linear search. A more efficient solution takes advantage of the fact that the letters array is sorted. This allows us to use a binary search approach to locate the smallest letter greater than the target. Binary search is effective because it significantly reduces the search space by repeatedly dividing it in half. Here's how it works: we start with two pointers, low and high, representing the bounds of our search. We calculate the midpoint, mid, and compare the character at letters, mid, with the target. If letters, mid, is greater than the target, we move the high pointer to mid 1 to search the left half of the array. Otherwise, we move the low pointer to mid +1 to search the right half. Once the search completes, the low pointer will point to the smallest letter greater than the target. If no such letter exists, we use the circular property of the array to return letters, low %n. This approach has a time complexity of O log n, because the search space is halved at each step, and it uses O1 space since only a few pointers are needed. Binary search offers significant advantages over the brute force approach, particularly for large arrays. It is highly efficient because it leverages the sorted property of the letters array to reduce unnecessary comparisons. Although the implementation is slightly more complex than brute force, the trade-off in efficiency is well worth it. This is why binary search is the chosen strategy. The key observations that make this approach optimal include recognizing that the array is sorted, which enables the use of binary search, and understanding the circular nature of the array. If no letter greater than the target is found, the smallest letter, which is the first element, becomes the answer. This is elegantly handled by returning letters, %n. The aha moment here is realizing how binary search avoids the inefficiency of linear traversal, achieving logarithmic time complexity, which is crucial when handling larger input sizes. When we compare the two approaches, the trade-offs are clear. The brute force method is simple and effective for small arrays, but its linear time complexity makes it inefficient as the size of the array grows. On the other hand, binary search is optimal for both small and large arrays because it leverages the sorted nature of letters to achieve a logarithmic time complexity. This makes it scalable and efficient even for large inputs. In conclusion, the binary search approach is the superior choice due to its efficiency and scalability. Its ability to handle large inputs quickly and effectively makes it the preferred strategy over brute force for solving this problem. To solve the problem of finding the smallest letter in a sorted array that is strictly greater than a given target, we begin by understanding the brute force approach. First, we take the input, which is a sorted array of characters called letters, and a target character. We initialize a variable n to store the length of the array. Then, starting with the first character of the array, we iterate through each letter one by one. During this iteration, we compare each character to the target. If we encounter a character that is greater than the target, we immediately return it as the result. This ensures that we find the smallest letter strictly greater than the target as early as possible in the array. If no such character is found during the loop, the circular property of the array comes into play. Since the array is circular, when no character is greater than the target, we return the first character in the array because it wraps around to become the next valid letter. The final step of the brute force algorithm is to return the result, which is the smallest character strictly greater than the target. Now, let's look at some key insights. The circular array behavior is a critical aspect of this problem. If no character greater than the target is found by the time we've scanned the entire array, the smallest character, which is the first element of the array, becomes the answer. This is guaranteed because the array is sorted and wraps around. The comparison logic, specifically the condition letters, I, target, ensures that the first valid character greater than the target is returned immediately. Since the array is sorted, this character is guaranteed to be the smallest. While this brute force approach is straightforward, it has a time complexity of O(n), as we may need to scan the entire array. This is fine for small arrays, but for larger inputs, we may want to explore more efficient methods like binary search. The sorted nature of the input array is a key advantage, as it eliminates the need for additional sorting and allows us to directly apply the logic. The output of the algorithm is a single character, which is the smallest letter strictly greater than the target. No additional data structures are required, keeping the implementation simple and efficient. Now, let's go through some important edge cases. When the target is smaller than all elements in the array, such as when letters is C, F, J, and the target is the first character of the array, C, is returned. If the target is greater than or equal to all elements, for instance, when the target is K, the circular nature of the array ensures that the first character, C, is returned. When the target matches an element in the array, such as F in the same example array, the next character, J, is returned. For an array of length 1, like regardless of the target, the only character in the array is returned. These edge cases demonstrate the robustness of the approach in handling various scenarios. Another edge case arises when all characters in the array are the same, for example, and the target is also a. In this situation, the circular behavior of the array means the first character, is returned. While the brute force method works well for small arrays, it can be inefficient for larger ones. This is where optimizations come into play. A binary search approach can significantly improve the time complexity, reducing it from O(n) to O log n. Binary search leverages the sorted nature of the array to locate the smallest character greater than the target by narrowing the search range. While the brute force method is simpler to implement, binary search is the preferred choice for scenarios involving large inputs. To summarize the brute force approach, we can use the pseudocode provided. The function iterates through the array, and as soon as it finds a letter greater than the target, it returns that letter. If no such letter is found, the first letter in the array is returned, ensuring the circular property is respected. Finally, let's analyze the complexity of the brute force approach. The time complexity is O(n), where n is the length of the letters array, because in the worst case, we might need to iterate through the entire array. The space complexity is O(1), as no additional space is used beyond the input array and a few variables for iteration and comparison. This makes the brute force method space efficient. While it is straightforward and works well for smaller arrays, for larger datasets, the time complexity becomes a limiting factor, emphasizing the need for optimized solutions like binary search. By balancing simplicity and efficiency, we can choose the best approach based on the size of the input and the problem constraints. The provided Python code solves LeetCode problem number 744, find smallest letter greater than target, using a binary search approach for optimal performance. The function nextGreatestLetter takes two inputs, a sorted list of characters, letters, and a target character, target. The goal is to return the smallest character in the array that is strictly greater than the target. If no such character exists, the search wraps around to the start of the array. Explanation of the code. 1. Initialization. The left and right pointers are initialized to the first and last indices of the letters array, respectively. 2. Binary search loop. The binary search algorithm is implemented within a while loop that continues until left exceeds right. The midpoint, mid, is calculated as the integer division of left plus right, //2. 3. Comparison and pointer adjustment. If the character at the midpoint, letters, mid, is less than or equal to the target, it means the desired character must lie in the right half of the array. The left pointer is updated to mid plus 1. Otherwise, if letters, mid, is greater than the target, the desired character might be in the left half, so the right pointer is updated to mid 1. 4. Wraparound handling. After the loop concludes, the left pointer will point to the smallest character greater than the target, if it exists. If left exceeds the length of the array, the modulus operator % ensures the search wraps around to the start of the array. 5. Return value. The function returns the character at the index left %len, letters. Edge case handling. If all characters and letters are less than or equal to target, the wraparound mechanism ensures the function returns the first letter. The algorithm handles duplicates and edge cases, e.g., empty target or letters list, gracefully due to the sorted nature of the input. Complexity analysis. Time complexity. The binary search runs in O log n, where n is the size of the letters array. Space complexity. The function operates with O(1) additional space since no extra data structures are used. This implementation is efficient and adheres to the constraints of the problem, making it suitable for production use. This is the Java implementation of LeetCode problem number 744, find smallest letter greater than target. The solution mirrors the Python logic using a binary search approach. The key differences include type declarations for variables and the use of Java's array handling. The algorithm efficiently finds the smallest letter greater than the target, wrapping around to the start of the array if no such letter exists. Here, we are solving the problem for the input letters equals C, F, J, and target equals C. First, we initialize two pointers, left at 0 and right at 2, which represent the indices of the first and last elements in the array. In the first iteration, we calculate the midpoint using the formula, left plus right, //2, which gives mid equals 1. The letter at this midpoint is F. Comparing F with the target C, we see that F is greater than C, so we move the right pointer to mid 1, which updates right to 0. Now, in the second iteration, we recalculate the midpoint. With the updated pointers, mid equals 0 plus 0, //2 equals 0. The letter at this midpoint is C. Since C is less than or equal to the target C, we move the left pointer to mid plus 1, updating left to 1. At this point, the loop exits because left is greater than right. The answer is determined by the formula letters, left %len, letters. Substituting left equals 1, the result is letters, 1, which is F. So, the output is F. In this example, the input is letters equals A, B, C, and the target equals Z. Initially, left is set to 0 and right to 2. In the first iteration, we calculate the midpoint, which is 0 plus 2, / 2 equals 1. The letter at index 1 is B. Comparing B with the target Z, we find that B is less than or equal to Z, so we move the left pointer to mid plus 1, updating left to 2. In the second iteration, with the updated pointers, the midpoint is recalculated as 2 plus 2, / 2 equals 2. The letter at index 2 is C. Again, comparing C with Z, we see that C is less than or equal to Z, so we move the left pointer to mid plus 1, updating left to 3. Now, the loop exits because left is greater than right. To find the answer, we use the formula letters, left %len, letters. Substituting left equals 3, the result is letters, 3% 3, which is letters, 0. This gives us A as the output. Now, let's consider the case where the target is smaller than all the letters in the array. The input is letters equals D, E, F, and target equals A. We initialize left to 0 and right to 2. In the first iteration, the midpoint is calculated as 0 plus 2, / 2 equals 1. The letter at index 1 is E. Comparing E with the target A, we find that E is greater than A, so we move the right pointer to mid 1, updating right to 0. In the second iteration, with the updated pointers, we recalculate the midpoint as 0 plus 0, / 2 equals 0. The letter at index 0 is D. Comparing D with A, we again find that D is greater than A. This leads us to move the right pointer to mid 1, updating right to minus 1. At this stage, the loop exits because left is greater than right. To determine the answer, we use the formula letters, left %len, letters. Here, left remains 0, so the result is letters, 0. The letter at index 0 is D, making D the smallest letter greater than the target A. Therefore, the output is D. The time complexity of the given solution is driven by the binary search algorithm it employs. Binary search works by repeatedly having the search space. At each step, the algorithm calculates the midpoint of the current range and decides whether to continue searching in the left or the right half, based on the comparison between the target and the middle element. This halving process leads to a logarithmic number of iterations, specifically log base 2 of n, where n is the size of the input array. Once the loop completes, the wraparound case is handled using a modulus operation, which is a simple constant time operation. Since the binary search dominates the overall process, the total time complexity of the algorithm is O log n. This makes it highly efficient for searching in sorted arrays. The space complexity of the solution is minimal, as it does not rely on any additional data structures or recursion. To begin with, the input list, letters, is passed as an argument and is used as is without creating a modified copy, so it does not contribute to extra memory usage. The algorithm itself uses a small, fixed number of auxiliary variables, such as left, right, mid, and a variable for storing the result. These variables occupy a constant amount of memory, regardless of the size of the input array. Since no other resources are allocated dynamically during execution, the total space complexity of this solution is O(1), making it extremely space efficient. To understand the efficiency of the binary search, it's helpful to compare it with a brute force or naive approach. In the naive method, the algorithm would iterate through the array one element at a time, checking each letter to find the smallest one greater than the target. This method has a time complexity of O(n), as it requires a full scan of the array in the worst case. However, both the naive and binary search methods have the same space complexity of O(1), as neither approach uses additional memory beyond a few auxiliary variables. The key advantage of binary search lies in its time complexity, which is O log n, a dramatic improvement over O(n). By narrowing down the search space logarithmically, binary search is significantly faster, especially for larger input sizes. The binary search algorithm maintains a consistent logarithmic time complexity across all scenarios, but it's worth exploring the best, average, and worst cases to understand its behavior. In the best case, the target is found near the middle of the array, which allows the algorithm to terminate after only a few iterations. However, even in this scenario, the logarithmic time complexity, O log n, remains the same, as the halving process defines the algorithm's overall structure. In the average case, the algorithm performs about half the maximum number of iterations, but the time complexity still resolves to O log n. The worst case occurs when the target is smaller than all elements or greater than all elements, requiring the maximum number of iterations. Despite these variations, the binary search consistently operates within O log n time. The logarithmic behavior of binary search can be explained mathematically. Starting with an array of size n, the search space is halved in each iteration. After the first step, the search space becomes n/2, then n/4 after the second step, and so on, until only one element remains. This halving process follows a geometric progression and completes after log base 2 of n iterations. This mathematical property guarantees that the algorithm runs in O log n time, regardless of the input size. The binary search method is thus highly efficient, leveraging the sorted nature of the input array to minimize the number of comparisons. Combined with its constant space usage, this approach represents an optimal solution for the problem, far outperforming the naive method in terms of scalability and efficiency. When solving this problem, there are a few common mistakes to watch out for. First, it's important to handle the circular behavior of the array correctly. If no letter in the array is greater than the target, you need to wrap around and return the first letter. Forgetting this violates the problem's constraints. Another mistake is using a linear search approach when the array is sorted. This misses the opportunity to optimize the solution with binary search, leading to an O n time complexity instead of the more efficient O log n. Finally, a subtle but critical issue is misinterpreting the equality condition. The prompt specifies finding the smallest letter greater than the target, which means the condition should exclude equality. Comparing with greater than or equal to would lead to incorrect results. These are key areas to keep in mind as you refine your solution. Building on this, another frequent issue arises from off-by-one errors in binary search. Mistakes in adjusting the low and high pointers can cause you to skip over the correct element or even create an infinite loop. Proper pointer updates are essential to ensure binary search converges correctly. Additionally, edge cases often trip up candidates. For instance, consider what happens when the target is smaller than the smallest letter or larger than the largest letter in the array. Failing to address these scenarios can lead to incorrect outputs or runtime errors. Thoroughly testing these edge cases ensures your solution is robust and ready for deployment. From an interview perspective, optimizing your approach is key. Interviewers expect you to recognize the sorted nature of the input and apply binary search, achieving O log n time complexity. Clearly articulating this observation demonstrates your understanding of the problem. It's also important to discuss how you handle edge cases, as this shows attention to detail. Be ready to explain how you manage the low and high pointers in binary search and why the condition letters, mid, target is used. Additionally, emphasize the space complexity of O1, which is optimal for this problem. If asked about brute force solutions, acknowledge their simplicity but highlight why binary search is preferred due to its efficiency and scalability. These points not only strengthen your solution but also showcase your problem-solving skills during an interview. There are also related problems that can help reinforce your understanding of binary search techniques. For example, in LeetCode 278, first bad version, you use a similar approach to find the first occurrence of a target condition. LeetCode 852, peak index in a mountain array, focuses on binary search with a different target condition. In LeetCode 34, find first and last position of element in sorted array, you locate boundaries using binary search. And LeetCode 704, binary search, is a foundational problem to practice the basics of this algorithm. When considering alternative approaches, brute force is an option with O(n) time complexity, but it's inefficient for larger arrays. A custom iterative search might also be possible, especially for creative indexing scenarios, but it's rarely used since binary search is more direct and efficient. For interviews, binary search remains the optimal choice due to its scalability and clear application of the sorted property. Great job on completing this problem. In summary, we tackled the challenge of finding the smallest letter greater than a target by using binary search for an efficient solution. Remember to practice binary search problems to strengthen your skills further. If you enjoyed this video, please like and subscribe to stay updated on more coding walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!